Good afternoon and welcome back to Dr. Logic Awkwardly Does Logic. After months and months, possibly even years of waiting, it is the moment of truth. Or rather, the moment of truth and membership, because I'm finally going to prove to you this lemma that I have promised you for so long. First, though, I'll give you a statement of it, and we shall rehearse or refresh your memory on some of the definitions that we might need to have in order to prove it. So the lemma is this. It says, okay, come on, get away from here, Zoom. There we go. Lemma. So we're going to let MS be the canonical model for some system S. And you'll remember from the definition that we just gave that MS is going to be constructed out of the set of all maximal S consistent sets, the R relation defined using that box minus construction, and the valuation, which just says that if an atom is a member of a set, then it is true at that world. Now, I'm going to drop all of the superscripts from now on, just because it makes everything easier for me to write and probably easier for you to read. So we've got this arbitrary canonical model, and what we are going to show is this. For any well-formed formula phi and gamma that is in the set of worlds for this canonical model, the value of phi at gamma is true. That's the truth side. If and only if phi is a member of gamma, and that's the membership side. So the proof of this result is a proof by induction. We look at formulas at different levels of complexity, starting with the basis case, which are the atoms, and then we have an inductive assumption that says, okay, suppose we've got two arbitrary formulas we've already proven this result for. We can also show that it holds for formulas of the next level of complexity. So our basis case, as I said, is going to be the atomic case. So phi is an atom, let's call it P. Then, we have that the value of P at gamma equals true if and only if P is in gamma, and we get this by definition. This is how we defined our valuation. So that is quite easy. Now, we're going to have our inductive hypothesis, which says let phi and psi be arbitrary formulas, and we will assume two things. First, that we have this result, that phi is true at gamma if and only if it is a member of gamma, and the same thing for psi. This is our inductive hypothesis. So now what we need to show is that if we already have things that the result holds for, and we construct something out of them, the result will still hold. We don't need to do it for each of the different types of constructions because some of them reduce to other ones. So we're going to prove the cases for negation, conjunction, and necessity, and leave the cases of disjunction, the conditional, and possibility as exercises for the viewers, because you can get negation and conditionals from conjunction and negation. Sorry, you can get disjunction and conditionals from conjunction and negation, and you can get possibility from negation and necessity. So you don't need to prove all 6 cases, just these 3. So let's consider the case of negation first. So we're going to consider the case of not phi. Now, we know that the value of not phi at gamma is true if and only if the value of phi at gamma is false. This just comes from the definition of truth. However, once we have, let me just change color so I can do some highlighting. This fact, so suppose that phi is false at gamma. Well, then this side of our inductive hypothesis is false because it is an if and only if claim. This means that this side has to be false. So if we suppose that the value of not phi at gamma is true, and since we're trying to prove an if and only if claim, we start by assuming one side and we try to derive the other, and then we do the reverse. So this is a reasonable assumption to make. Then, by the definition of truth and the inductive hypothesis, we know that phi is not a member of gamma. But, sorry, not phi. Gamma is maximal. This means that for every formula, either it or its negation is a member of it. So if phi is not a member of gamma, then it has to be the case that not phi is. Excellent. So from assuming that not phi was true at gamma, we were able to show that it was a member of gamma. We also have to go the other way around. So now, suppose that not phi is a member of gamma. Now, gamma is not only maximal, but it is also consistent. And so we know that phi is not going to be a member of gamma, because otherwise it would be inconsistent. And now we can just kind of unwind the same steps that we had. So if this is false, then this has to be false. But then if it is false that phi is true, we get that not phi has to be true. So that is quite straightforward. Now we'll consider the case of phi and psi. Again, we'll start off by supposing that the value of the conjunction at gamma is true. By the definition of truth, we know that each of the conjuncts has to be true. And by now, hopefully you can already see how this is going to go. Again, we go back to our inductive hypothesis. Now we have that this is true and that this is true. So because these are biconditionals, this means the right-hand side has to also be true. So by the inductive hypothesis, phi is a member of gamma and psi is a member of gamma. Now you may recall, hopefully, a lemma that we proved a while ago, which says that in a maximal consistent set, if phi and psi, if two separate formulas are a member of a maximal consistent set, their conjunction has to be as well. So by the earlier lemma that we proved a while ago, we know that the conjunction has to also be in gamma. And now here, we actually can just completely read this in the opposite direction to get the other way. So every one of these statements is actually an if and only if claim. So if we have, suppose we assume that phi and psi is a member of gamma, then by an earlier result that we've proven, we know that each one of these has to be a member of gamma, but then these sides of the inductive hypothesis are true, which means that their valuations are true, but if the two conjuncts are both true, then the conjunction has to be true. So the propositional cases are easy. As I said, I will leave disjunction and conditional for you to do on your own. Of course, it's necessity that is the interesting one. And this we are going to have to kind of do in the two different directions because we'll appeal to different results in different parts of the definitions. So I'm actually going to start from membership this time. So we're now going to prove the case for necessity. And we'll start off by assuming that box phi is in gamma. Now, by the definition of the accessibility relation in a canonical model, we know that phi is going to be in delta for every delta that is accessible from gamma. So every delta that gamma can see. But look, our inductive hypothesis held for all maximal consistent sets, so it also holds for delta. So by the inductive hypothesis, we know that the value of phi at delta is going to be true, again, for every delta that is accessible from gamma. And this is exactly what we need in order to get the truth of the necessity claim. So from here, it follows by the definition of truth that the value of necessary phi at gamma is true. So there's one side. That is going from membership back to truth. Now we want to go from truth to membership. So let us start off by supposing, actually, we are not going to suppose that it is true and then show that it is a member. What we're going to do is we're going to suppose that it is not a member and then show that it has to be false. So now we're going to suppose that that necessary phi is not a member of gamma. Because gamma is maximal, we have that not necessary phi is a member. Again, every formula or its negation is in a maximal consistent set. So if box phi isn't in, its negation has to be in. Now, this is where, again, one of the earlier lemmas that we've proven comes into play. There was a reason for all of the things that we did. By this earlier lemma, whenever we have a negated necessity formula in some maximal consistent set, we know that the box minus of gamma along with not phi is consistent. So it is contained in a maximally consistent set. That is from Lindenbaum's lemma. Let's call that set lambda, just so we don't confuse it with our previous one. But by our definition of the accessibility relation, we know that gamma can see lambda. Lambda is accessible from gamma. Now, this here, this not phi is a member of lambda. So I'll just make this explicit. So remember, not phi is a member of lambda. And we've already proven for not phi that so we've just shown earlier in this video that not phi will be a member of lambda if and only if not phi is false at lambda. But gamma can see lambda. So gamma can see a world where, because not phi is the member, that means that phi is the one that is false. So gamma can see a world where phi is false, but what does that mean? That means that phi cannot be necessary at gamma, i.e., the value of it is false. And now we can kind of turn this around through contraposition, and we get that if the value of necessary phi is true at gamma, then necessary phi has to be a member of gamma. That is it. the wonderful, wonderful, magical, mystical, exceptionally cool truth and membership lemma. It's cool because what we'll be able to go on and do with this when it comes to proving canonicity and completeness of various logics. But what I find really cool about it is that it shows how if you set up your definitions right, everything just falls out. It kind of reinforces just how important our definitions are. And a lot of times, like when you're doing research in logic and you're trying to figure out results, it's a lot of the process isn't so much here are my axioms, here are my derivations, but rather, what are the definitions that I need to have in order to be able to generate the results that I need? So actually, definitions, they may seem boring and tedious, but are in fact super important. So this was a really long video, but I hope it was interesting and worth the wait, and the cool things with this lemma in just a little bit. So take care and see you then. Cheers.